Alright everyone, I thought we'd try something different today, which is to go on a field trip, except that we're not going to actually go anywhere or do anything. What I wanted to do is show you a real-life example of particle-in-a-box phenomenon, in this case semiconductor quantum dots. Here you see some models. These are drawn on a computer, but what these are basically just large clusters, a couple hundred atoms big, a couple of thousand atoms in some cases, maybe even up to a million atoms of just semiconductor particles. You can image these in an electron microscope, so you can see that here. And you can see why we call these quantum dots, is because they're round. And they're round for the same reason that a bubble is round. It's surface tension. That's not to say that you can only make dots. If you get the formulations just right when you synthesize these, you can make rods and wires and all kinds of shapes. Here you see something that, I know it kind of looks like a boomerang. It's actually got three legs. The third leg is just pointed up at the microscope. So we can make all kinds of sizes and shapes of basically every semiconductor that exists. So that's all fine and good, but so what? It turns out their optical properties are absolutely incredible. Now, here you see on the left, these are the absorptions, and the small dots have an absorption here in blue, where the absorption onset is at a high energy blue wavelength. Now that compares to a larger dot, which has an absorption onset towards the red, and we all know that red photons are lower energy than blue photons. So the large dot has lower energy absorptions, and that's all mirrored in the emissions, where again the small dot is a blue high energy photon emitter and the large dot emits red. And here in this photograph, this has not been doctored up in any way. This is what these materials really look like, except for, actually, this is kind of interesting, they look better in person than they do, compared to what you're seeing, because your monitor cannot correctly express how color saturated these things look. That they have very high color purity, and unfortunately your monitor can't mimic that. So they actually look more, they're actually prettier in real life. Now, in terms of what these things are useful for, the QLED TV, go to Best Buy, those are sitting in the back. Those are from Samsung. So we're putting these in monitors. I believe the Kindle Fire has them. And guess what? The greens, yours truly is one of the developers of the green color in these displays. Now, the materials I made, I even have a patent on it, they don't use those anymore, but I did have something to do with this, and if any of you come to office hours, I can tell you the whole story later. You can also do bioimaging with these, and this is another example out of my research lab where you see us staining cancer cells with quantum dots. And the reason that this is useful is that the quantum dots never photobleach. Dyes photobleach. They'll photobleach within minutes, but my quantum dots never do. So you can study biological processes much longer. All right, now as for how the particle-in-a-box principle applies, here we have a little, I know it's kind of silly, but this is a large quantum dot, and you can see the valence state, which has all the electrons, and this being a big red dot, if a green or blue photon comes along, the electron absorbs that, and it goes to a higher energy state, and that absorbs the photon. So I know you had this in freshman chemistry. So when the electron relaxes back to the valence state, of course that energy difference results in a red emitting photon. All right, now, particle in the box says that these energy levels depend on the size of the box. So if the box gets smaller, the energy levels will rise. So watch this. You see that energy rises as the box gets smaller. So that means that you're going to need a higher energy blue photon to cause that electron to get excited to that higher state. And of course, when the electron relaxes, you're not going to get a red photon. Of course, you have to get a higher energy blue photon. So that's how these materials work. Now I want to show you one other thing that's kind of interesting, how we synthesize these. So me and my postdoc made a video that's coming up next. Alright, so here you see us weighing out some of the chemicals. In this case, this is the solvent. It's okay that the solvent is a solid at room temperature because we're actually going to do this reaction at 350 degrees. We also have to prepare some of the chemicals inside of an inert atmospheric glove box because some of them would violently explode if they were ever exposed to air. So we're going to put all these chemicals into the round bottom, and then we're going to heat up the round bottom, and we're going to briefly expose it to vacuum to remove any traces of air and water that may still be inside of the solvent or chemicals. Now once that part is done, we put it under a nitrogen atmosphere and heat it up to 350. We remove the heating mantle and make sure that it has good contact with the stir plate, because we got to make sure that the stirring is pretty robust as we inject the semiconductors, as you see here, and that color change is the quantum dots forming. The injection at first at high temperature allows the quantum dots to nucleate, and the temperature cools a bit after the injection, which allows them to grow to all the same size. Here we've designed the prep to produce a green emitting quantum dot, as you see here. And so that's how you do it. It's actually a pretty simple process.
All right, everyone. I hope that video was interesting. You know, one of the reasons that they have research faculty teach classes is this idea that someone like myself will bring like the latest and greatest, in terms of like what's going on in the world of research into the classroom. The problem is that completely fails, like most things. Yeah, that was dark, wasn't it? Anyway, like most things, it fails because as time passes, like the curriculum for this class was all developed in the 1930s. Seriously, you're learning the same thing that students who sat here in the 1940s, you're having the same class. And I imagine 100 years from now, it's still all the same. Every year that passes, the storehouse of information in scientific journals just gets bigger and bigger, such that there's a greater disconnect between fundamental things that you have to know about to what's being done in the research lab. So it's hard for me to bring anything into the classroom because every moment that I do that takes away time from something else that's considered more fundamental. Anyway, just so you know, that's how this place is set up, that's the idea. And what's also kind of messed up is that I'm really here to win grants. And sometimes if you had faculty members who were distracted or unresponsive, and they were research faculty, well, I don't know those people, I'm not trying to defend them necessarily, but I hope you understand that often I've got a grant application due, and it's not uncommon for faculty to be like, well, if I lose this grant, my career's over. So how much more important is that to them than teaching your next class or double checking your exam grade, right? That's also why some of the dysfunction occurs in the university. Since I'm getting an MBA, I can tell you one of the first things they drill into our heads about business is that business changes constantly, generally to become increasingly efficient. Not necessarily, but that hopefully is one of the ideas behind capitalism. Universities never change, right? It's still the same from the 1930s. We got more computers and better lights, LED lights. But how much does that really matter? Well, the computers are cool, but anyway, I actually predict that, especially accelerated by COVID, that universities are going to change a lot. Not next year, but maybe like in a 10-year time frame. I bet the way we do business at the university is going to change drastically. But anyway, this is a chemistry class, so maybe I ought to talk about chemistry stuff because I've already wasted enough time talking about showing videos of quantum dots, and I hopefully sneaked a cat in here or two. I haven't actually made it yet. All right, as usual, let's review. And as I mentioned last time, every time I have a class, I can't review from the very beginning anymore, and it gets further and further away. So I can only review what we talked about last time. So if you're not keeping up at a decent pace on these videos, on the class itself, you're going to be left in the dust. So what we talked about last time was the uncertainty principle. And before I mentioned the mathematics of the uncertainty principle, which actually is right here, I wanted you to understand in terms of position and momentum why it works the way it does, which is that when I take this wave function, this delocalized wave function, so it looks like a particle in a box, and it's as spread out as it basically could be in this box, I would decompose this to e to the I kx, where these k's are, that's a low k, and that's a higher k, and that's the highest k. So slow wave, faster wave, fastest wave, and these sum up into that. And that means that when you're measuring momentum, you're going to either measure k1, k2, or k3. Now, when it came to the localized state, and remember my little computer graphics last time, I showed you how I had to add 5 e to the ikx waves. And so, slow, a little faster, faster, fastest. There's more states, so there's less certainty because every time I make a measurement, I'm going to get one of these 5, whereas before I used to get one of 3 results, making me much more certain because I always get one of 3 numbers. And here, I'm always getting one of 5 numbers every time I make a measurement. So I certainly don't feel as certain about this one. Also, we talked about how, and as the example showed, why this one is actually a higher energy than that one, because these momentum waves that are necessarily part of it, these can only go higher in energy. And again, you saw that in the video, an actual manifestation. Last thing we talked about was the mathematics of that, how the variance in position and momentum is related to this commutator, a quarter of a commutator squared. We talked about how to evaluate the commutator. I'm going to give another example, and then we're going to finish this up of a commutator. Now, we did position and momentum, but the reality is this is something, I know you've heard the Heisenberg uncertainty principle. You can't know where something is and how fast it's going, and that was this, and we worked all the way through this, right? We showed that, we talked about how to evaluate a commutator, and we saw that the value was h bar squared over 4, right? Blanking out, over 4. Okay, now that you seem to be graduates, graduating with a degree in science and engineering math, blah, 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 there's actually more than one Heisenberg uncertainty principle. There's like hundreds of them. It's just the popular literature, it just sounds good. You can't know where something is and how fast it's going. It just sounds good. But reality is, what you do is, I mentioned that there's really a bunch of operators. You know the Hamiltonian operator, you know momentum squared, position. Technically, position squared, that technically counts as a different operator. That's actually true. There's angular momentum in different directions, total angular momentum, flux. There's really a bunch of operators. Anything that can be measured has an operator. So what happens is, if you plug in any 2 operators and you get a non-zero commutator, you have an uncertainty principle. So there's actually uncertainty principles everywhere. I'm not going to bring that up again. We're just going to talk about x and t, and then they need little hats. Little hats. Anyway, operators don't have hats. And so just so you know that you can actually have more than one uncertainty principle. But there's no need. Go to grad school if you really want to know more. But actually, I will work one. I'm going to work one just so you understand commutators a little bit better, because that's a tough one. And then we'll be done with this, and we'll start talking about a new subject, which is when we're going to start talking about things beyond the free wave. Now, remember, the free wave is when potential energy is 0. We're going to start introducing like a problem that has potential energy in it, and we're going to complicate that further and further until we get up to a hydrogen atom, and then we're done. And then we definitely are done because that's the end of the semester, by the way. Okay, so one more example, because I want to make sure you know how to do these commutators. I've already done x and p. Watch the last video if you forgot that. But what I want to do is, tell you what, let's do position, because we're familiar with that. And the other one, what am I doing? Let's do Hamiltonian. That's an operator. It's technically the square of the momentum operator over 2m. All right. And 2m is a constant, so that's like, constants are not operators, right? They're just constants. All right. Now what I want to do is do the commutator with these 2, and just to show you how it works. Whoops, sorry, problem with the camera here. All right, what was I saying? I was going to do the commutator of position and kinetic energy, p squared over 2m. All right, p squared over 2m. Commutator, and what is that? Okay, so I'm going to bring all this up again. Remember I told you that there's a couple of traps you can fall into. Let's see here, I've got x. Now p squared over 2m is minus h bar squared over 2m. Double derivative. And we're still just in one dimension. When we go to more dimensions, that's actually not as hard as you might think. Okay, then minus. You gotta be careful here. Minus, because that's what a commutator is. Operator 1, operator 2, minus operator 2, operator 1, minus. But I've got a minus from the kinetic energy. That's actually a plus. So gotta be careful with that. I will factor out all these constants here in a second, because that's just going to be way easier. All right. I said this last time, but it bears saying again. There's a way that the people who get C's in this class distinguish themselves as getting C's because they look at this, completely forget what I told them, which is that what does this look like? Oh, double derivative of x. Well, derivative of x is 1, derivative of a constant 1 is 0. So therefore this is 0. This is double derivative of nothing. So I'll make up a rule that the derivative of nothing is 0. And I don't mean nothing, I don't mean it's the derivative of 0. That would actually be 0. This is the derivative of empty space. Now that corresponds to nothing. Like, I don't mean nothing isn't 0, it means that you have an unanswerable question. This is a stupid question, it can't be answered. It's not even a question, it's just an is. So if you are taking something that has no definition and giving it one, calling it 0, you've messed up. Despite the fact that I'm telling you this right now, 1/3 of you are going to do it anyway. The way around this trap is to apply a dummy function, and if you're going to multiply by a dummy function, you have to divide by a dummy function, and that way it gets rid of it. The trick is that you do one on the right, and then you divide out on the left. Now remember, I told you last time, you're going to see this over and over again. In just about 2 weeks, you're going to see this multiply and divide thing over and over again. So you want to get used to this. And this is how you answer these questions. I'm sure I'll have a question like this on the exam. All right. Now with this said, let me factor out some constants. And you can see that the complexity comes from the fact that we're going to have, here, let me write it down. We're going to have a product rule. Okay, so here's this. Now I'm going to factor out the constants, just because that's a little bit nicer. And I've got x double derivative. If I factored out a minus, then that's a minus, right? God, that kills me sometimes. Okay, now remember the next problem, the next way that the people who get C's distinguish themselves is this gets applied to both of these, right? So there you go. And what happens is you can see where the complexity comes in. You've got yourself a product rule. Product rules always complicate things, unfortunately. And remember, a double derivative is a derivative and then another derivative. So we've got a product rule and then we got another product rule. Okay, but remember, that sucks, no doubt. But if you can do this, you are worth a lot of money. I mean, you can all do it. It's a matter of being patient enough. And if you're patient enough, careful enough to do this, you're worth a lot of money. You're going to make a lot of money. You all can do it. It's just a matter of your patience, your ability to delay gratification. Hopefully you've heard that before. The ability to delay gratification is the #1 predictor of success. Okay, so I'm writing the constants down. Now this first term, there's not much you can do with it. It's just an is. It's just a double derivative. But you know what? I bet something's going to happen with it because we got ourselves 2 product rules. And that's going to do some stuff. Okay. First derivative, second derivative. I can kind of do that in my head. It's a bit painful. Derivative of x is 1. I leave the other guy alone. Then I leave that alone. And I do the derivative of the wave function. I gotta be careful that I keep track of all my brackets. Let's see, I guess I got enough room for one more. Let's see here. And this will finish it. It's just that I'll have to, I definitely need to try to simplify it. Again, this first thing, there's not much I can do. It's just the double derivative of the wave function. Okay, now what I've got is the single derivative of the wave function. And again, there's not much I can do with that. It just is. Okay, now what? Okay. Derivative of that, leave it alone. Okay. Then, leave that alone, derivative of that. Minus, that minus carries. Okay, so that one, now I leave that one alone, and then I do the double derivative. Oh, it's a double derivative, right? It's a derivative of a derivative. Okay, so let's see here. In terms of canceling, that and that. And so what do we get? We get 1 over psi minus h bar squared over 2m. Just the derivative, 2 times the derivative of the wave function. I just factored the 2 out. Oh yeah, I don't need any more brackets. Okay, and let me double check, is that correct? Yeah. Okay, so this again is the commutator of x and p squared over 2m. Okay, now this is a good lesson in how this stuff works, and I have to admit, this bothers me. The name of the game in the uncertainty principle is it 0 or is it not? Well, I don't like the fact that I've got a function and a derivative of a function, but all that matters is not 0. Okay. As much as I don't really know what this is, I know it's not 0. Okay, that means that x and basically p squared, the 2m doesn't matter, I'll include it anyway. They have an uncertainty. There's an uncertainty principle between the two. Okay, now let's put that in more language that a high school student would understand. The more certain I am in position, the less certain I am of energy, right? Now actually, doesn't that go back to our examples up here? The more certain I am of position, the less certain I am of energy, where energy being measured as kinetic energy, right? Kinetic energy is energy. I just talked about this at length last class and this one. Certainty in position, less certainty in energy. I gave that example of those quantum dots. Certainty in position and the smaller dot led to greater uncertainty in energy, which also means, for the examples I gave, that the energy increases. And that's why the smaller QDs are blue and the bigger ones are red. So we're seeing that we're seeing all of this being worked in different ways, but always coming to the same conclusion about position in momentum or momentum squared. And yeah, they always, one goes up, one goes down, just like this. Right, so it's all kind of consistent. Again, the only thing that's a little funkalicious about this is how this is not, I want it to be like a number. I want it to be like h bar squared over 4, something like that. But it didn't come out that way, but it's still not 0. And again, that definitely means that there's an uncertainty principle. The more certain I am in position, the less certain I am in energy. And if I'm less certain in energy, then I have more energy. We've seen examples here, and we saw an example in the little video. It all makes sense. Even when your approach is very different, it all makes sense and it's all consistent. All right. With this, we're going to take a little bit of a break, and we're going to start on potential energy now. All right, so give me a minute. I'm going to wipe out the board, and we're going to introduce potential energy, and it's going to be light. And then it's going to get more complicated in the next class, all right? But today, hopefully, it's kind of an easy day. So give me a minute to wipe out the board. All right, so I'm back. Okay, so today we're going to start building up model problems where the model is defined by potential energy. Potential energy is what distinguishes a free wave, which is quite literally nothing, to a hydrogen atom, which is pretty complicated. And that will be the last thing that we even try. It's that complicated. Okay, so the way to start this out is I'm going to start with flat potential. So let's draw, and you've actually already seen me do this. Let's draw a potential surface. So potential energy rises. It'll be 0, which is what we've been dealing with this whole time. And what I'm going to do is I'm going to put a little bump in it. Put a little bump. And it'll keep going to the right forever. Obviously, I can't draw that. Now, you may recall that I was previewing a little bit about this. When I mentioned that, what happens is that the free wave, which is wavy because it has lots of kinetic energy, in this case it has a lot of kinetic energy, what happens is once it hits a barrier, it gets less wavy. Its wavelength increases, which of course means that the kinetic energy has decreased. Now that makes sense because it lost some of its energy, not much, but it lost some of its energy to that step. That potential energy ate some of its kinetic energy, so it's less wavy, right? So I showed you that before, and I'm showing it to you again. And listen now, visually, right? We try to do things visually, now let's do it mathematically. I also want to point out that this is actually 2 graphs in one. This is a graph of potential energy, and on top of that is a graph of the wave function. That is going to come up a couple of times because I've seen people badly misinterpret these things. Like one time I had a person say, "Oh, well, it looks the way it does because it can't hit the wall." These are 2 different graphs. This is a wave function graph, and on top of it is the potential energy graph. It's meaningless for the 2 graphs to overlap in any particular way because they're 2 different graphs. Now, I'll give some more explicit examples in the future. I'm just previewing. I want you to get that idea in your head because that is something when we get to more complex potential surfaces and people start talking about how the wave function hits the potential, looking at the graphs, that's nonsense. So anyway, that's not important right now. I just want to get that idea in your head. All right, so let me write out the Schrodinger equation. So I'm going to write out the energy equation, and I'm going to include potential energy. So, of course, as always, here's kinetic energy. And we're still in just x, so things are still relatively easy. Okay, now we've got potential energy, and when I put a little d naught, that just means it's like 5 electron volts, something like that. So it's just a number, and that has to be equal to the energy times the wave function. So this is just to a mathematician, this would be a relatively easy differential equation to solve. Now, because this is a number and energy is just a number, here's what you do. And I think in this extra hour, I think it's this week, or it'll be the next week, where I'll show you how you actually solve differential equations. All right, so anyway, what I'm going to do is I'm going to bring that over. Oops. E minus V naught. So there you go, right? It was really quite trivial. Just like I said, just like I visualized, but here's the equation. What happens is, with this potential energy deal, all that happens is it just sucks away some of the energy. So I could have told you it was a free wave and just said it has less energy to begin with, and you would have drawn this, or I could have just said it had more energy and you would have drawn that. But with the step barrier problem, you just have to make sure that the 2 are connected. That's all you do. So very, very simple. Okay, now again, I believe that it is this Friday in the extra hour because of how weird this is. There's no good way for you to ask questions, you know that. But I'm not going to just throw those hours away, forget that. For your own education, I'm going to show you how mathematicians solve this. It's not part of this class, but it's a good thing for you to know. if you're good at math, you are valuable. That is a good skill to pick up. And I know you're thinking, oh, but I really just don't want to. That's fine. I hope you really don't want money either, because that's just how it works. The more you put in, the more you get. So I'm going to show you how to do this. The solution is going to come out like this. So that's why you don't have to attend. You know what I mean, attend. Did I say attend? Okay, anyway, when I show you how the math majors solve this in DiffyQ class, which I know you didn't have, but I'm showing you, you get this. A is just a constant, and guess what? IKX, oh, you gotta love that IKX, plus B e to the minus IKX. So, for the differential equation that looks like this is the solution. Now, here's the thing. Because A and B are constants, they could be different things. One could be 1, one could be 0, yada, yada, yada. It depends on the nature of the problem. So as much as, remember I said that this is the general solution. So the more that we build complexity into the potential surface, you might have to start trying to think about, well, what exactly are A and B? In fact, you have to do that with every problem. So let's go ahead and do that. So anyway, I also should mention, of course, that the energy, remember that once you get wave functions, you need to plug them back into the Schrodinger equation, and of course you get the energies out. And in this case, of course, it's always, at this point, I guarantee you that we will see things for which the energy is not h bar squared k squared over 2m. We'll have model problems with that. I know that's like always the energy, right? Anyway, okay, so back to task. When we start to build some more exact pictures, as we start to add complexity to the potential, you might have to figure out what A and B are. And again, you actually do. Okay, now, and I'll show you how you go about that, which is to say that there's some like boundary condition. Actually, I alluded to it a minute ago. Remember when I said like, oh, you just have to make sure that this wave touches that wave, that it's like smooth and continuous? Smooth and continuous, remember that? You remember how wave functions have to be smooth and continuous? If I set up this problem and I gave you some numbers, like I told you what the mass is, I told you that this is at 5 nanometers, you know, if I'm giving you stuff to work with, you can actually start to figure out what A and B are such that the wave function is smooth and continuous. Again, previewing. We're actually going to do that next lecture. Okay, so given the nature of the problem, you can figure out what A and B are. Let me give you a couple examples of what you might find. A is equal to B. Okay, now if that's the case, guess what? The wave function is actually, I screwed that up. The wave function is basically cosine, right? Remember, 1/2 e to the ikx plus 1/2 e to the minus ikx. If A is a half, B is a half. If A is equal to B, your wave function is cosine. Likewise, if A is equal to minus B, then the wave function is sine. Now again, the reason A will be equal to B or A will be equal to minus B is because it will come out of from working the problem. The way the problem is set up, you'll naturally be led to one of these conclusions. Now remember, sine is 1/2i e to the ikx minus 1/2i e to the minus ikx. So 2i minus 2i, then you got yourself a sine function, right? So now if A is 1, then B has to be 0. That's due to normalization, and the wave function is, of course, even. I mean, I just explicitly stated that. Remember that this is a right wave. Right wave. A right moving wave, and of course, I won't write it down. If A is 0 and B is 1, then the particle is a left wave, right? E to the minus ikx. I won't even write that down. Okay, that's kind of obvious. Okay, so tell you what. How much time do we have? I have a few minutes. So I have been talking about the particle in a box for a very long time without ever formally introducing it. So why don't we go ahead and Yeah, I've got it. I've got 5 minutes left, so I'll use the other board. So particle in a box. So I am finally introducing that thing I've been talking about nonstop for like 2 weeks, right? Okay, so the particle in a box is technically, okay, this is kind of nutty, and don't forget this. It's a free wave. It's a free wave with walls. Okay, so at x equals 0, there is remember I'm drawing a graph of potential energy from 0 to L. So this is one graph, this potential energy, and what it's saying is to the left of 0, the potential energy is infinity. To the right of L, the potential energy is infinity. Now inside of that, I'm going to like with like a piece of cellophane, right, some clear plastic, I'm going to draw another x-axis and I'm going to draw the wave functions, right? But I'm putting that on top of this one. And that looks like this. Okay, now that is a valid solution to that's actually the ground state of the particle in the box problem. And the way I know that is, let's see, ground state x. Okay, so the way I know that is that I guarantee you that because it is it's a flat potential surface between 0 and L, that means it's technically a flat potential problem. It's technically a free wave. And the general solution is like what I've just been talking about nonstop for the last 5 minutes. This is the general solution. And I know what I've drawn and I know that those are consistent. Okay. Now I just said quite a bit that you have to make this conform to that, which means that you manipulate the A and B. So where does that come from? All right, now, part of the particle in the box problem of having infinitely high barriers to the left of 0 and to the right of L means that the wave function has got to be 0. Right? It's got to have nodes at those points. It's got to be 0, and it stays 0. Now, that part you don't have to worry about, but it's got to be 0 at 0. The wave function has to be 0 at 0. If it's not, then it has to have, then it's slightly penetrated the barrier. It can't do that. All right, so that means that the wave function at x equals 0, psi is equal to 0, is equal to a e to the 0 plus b e to the minus 0, which is 0. E to the 0 is, oh, that's right, no one's in here. E to the 0 is 1. Use your calculator if you're not sure about that. Look at if you need that as an identity. It's on the next test. Hopefully I've convinced you of that. So what I've got 0 is equal to a plus b. Therefore, a is equal to minus b, and the wave function is sine kx. There we go. You see, this is how you whittle away at a problem to a solution. Notice we're not quite done yet. K is rather unsatisfying. I mean, K is K. Remember, it's technically, remember that, have you forgotten this? It is 2 pi over lambda. You remember that? Okay. But you know what, though? The reason I say it's unsatisfying is I really want to see parameterization of the problem in the solution. And I have this thing has an L in it, and I bet you that's related to the wavelength, but it's not straightforward. It can be figured out, which is exactly what we're about to do. But again, I want to point out that when I set up a problem, the parameters of the problem need to appear in the solution. It's cool that I got a sine function, but I got to figure out what K is, and that means I got to figure out what the de Broglie wavelength is. And once I've done that, I'm done. I forgot about normalization. You have to normalize it, right? Okay, we'll do that in a second. Okay, now the way to do this next part, figure out K, is apply the second boundary condition. There's 2. The wave function is 0 at 0, but it also has to be 0 at L, right? So, okay, so here's the second boundary condition. At x equals L, the the wave function at L has to be 0, which is a e to the I k L minus a e to the e. You know what? What am I doing? What am I doing? I've already shown it's a sine. I'm just not thinking. Sine 2 pi over lambda L. Okay. No. I was just reproving what I already proved, sorry. Okay. I can figure it out from here. Okay, now how do I do that? Sine of an argument. Now remember, maybe some of you don't remember that word. The argument of a function is what you stuff into its face. Okay, so for sine, the argument to be 0, the argument has got to be, oh god, let me remind myself, 0. Oh, but we've already done 0. Well, I'll write it down anyway. 0. The next one's at pi, then sine of 2 pi, and on and on and on. Okay, so that's where sine is 0. So you see what I got to do is I got to make the wavelength, I got to make those innards 2 pi over lambda times L. I've got to figure out lambda to wipe out, to ultimately give me, it looks like pi. Pi is 2 pi, right? Let me check my notes here. I don't need my notes enough. Okay, now we can forget 0 because we've already done that one here. We did that one here. We did 0, 0. Okay, so let's figure out what lambda is. And again, we've already done that one, so forget it. Okay, so if lambda, now I just have to look at this. If lambda was 2L, and I've got 2 pi L over 2L, which would be pi. Let me look at my notes in case. Okay, yeah, there we go. All right, now let's do the next one. 2 pi. How is that? Okay, so if lambda was L, then that would work. Yeah, that's right. Tell you what, let me do one more. Okay, so what would L be? Lambda be? That would be 2/3 L. Is that right? No, 3 halves. What is it? 2/3. Oh, that's right, 2/3. Yeah, 2/3 L. Okay. Now the reason I'm doing that is I'm trying to find the pattern. Okay, so what's the pattern? And again, we're not technically lambda is infinity for 0 anyway. So we're forgetting that one. Okay, now what I can see here is that the pattern is, it looks like it's 2L over an integer. 2L over 1, 2L over 2, 2L over 3, right? So let me make that more clear. Right, see that? 2L over 1, 2L over 2, 2L over 3, on and on and on. So I can say that looks like 2L over some number, a mode number, right? Just like Planck, where that goes from 1, 2, 3, there we go. Okay, so there you go. All right, now with that, let me write down, sorry, I ran out of, this is the end here. I think I'm almost out of time. So let me just write down the end result, and let me just, because I'm out of room, I don't want to wipe out the board again, that's kind of stupid. So let's write down the solution, which is, shut up, Siri, shut up. God, anyway, so I'm out of time. Okay, so I will end with this. The wave function is sine of, okay, if lambda, so that'd be pi nx pi x over L. Is that right? Let me double check that. Yeah, that makes sense. Right, so this is 2 pi over lambda. Sorry, I got myself pretty confused there. Let's see. 2 pi over lambda, where lambda is 2L and x. So that's pi n x over L, pi n x. Okay, yeah, that works. So that just goes to show you, you just saw me get completely confused on some simple algebra. It can happen to you too. Just slow down and write everything out explicitly and just be careful how you cancel things. Okay, so anyway, one boundary condition gave us a sign. The other boundary condition told us what kx was. K is n pi x over L. Now, you know what? You just saw me work through it exactly, but you also, in all honesty, you could have looked at the ground state, you could have looked at the excited state, and probably just figured it out. And that brings me to one last point, and I'm going to end here. This is no longer the ground state. This is just the wave function. And notice that it depends on this, this mode number. This was a mode number when we were doing Planck, but when it's quantum mechanics, it's called a quantum. It's called a quantum number. Okay, again, it's exactly the same thing as a mode number from the Planck distribution. It just, I'm not kidding, it just has a new name, but it's the same thing. But it does reveal one new thing. Now, we know that there are ground states and excited states. Take the ground state of the hydrogen atom. This is the 1s state, right? Remember from freshman and organic? The excited states, there's technically an infinite number, but that includes the 2s state, the 2p state, the 3s, the 3p, the 3d. Those are excited states. So, in the particle in the box, which is kind of like a bad model for an atom, the nx equals 1 is the ground. It's a ground state, and let's say that you were to do some kind of spectroscopy and absorb light, have this thing absorb light, it would go to the nx equals 2, 3, 4, and those are excited states. So you can think of this as like a hydrogen atom. It's not really a good model for a hydrogen atom, but it does have it shows how like the ground state could be like a 1s state. In the excited states, there would be an infinite number, and those could be like a 2s and a 2p and a 3s and yada, 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 like I just said. So you're seeing quantum mechanics give you ground and excited states. And you do that by, you get your model system. You have some way of knowing what the solution looks like, although you're often missing an A or a B, and you use boundary conditions to work it all out, and that's it. Now, I'll begin next class by reviewing this because I want to point out something very important, something I didn't spend an entire lecture on. It's not normalized. Remember that? Remember how I said that you often figure out wave functions not using the Schrodinger equation? That just happened. And the thing you got to look out for is the normalization. All right, so I'm definitely out of time. So next time we'll review this and we'll do the normalization, and then there's a couple more fun problems we can do with that. So I will see you all on Friday.